So, hello, my name is Yaro Balhaj. I'm going to be presenting the water filtration tank design. So, to start off, the situation that we have is that an earthquake happened and basically caused the water to be contaminated with dirt, etc. So, our goal is now to filter the water with the least amount of material that we can use and a material that is strong enough to withstand the water pressure and a material that is light enough to be carried by people. So the contamination level is the concentration of the contaminant is 600 milligrams in the water. And we need to decrease that to 10 milligrams in order for the water to be drinkable. And it's fine if we decrease the water to less than 10 milligrams, but the goal for now is 10 milligrams. Okay. So in order to fix this problem, we know that we need to know the number of the trays that we're going to need to design in the tank in order to filter the water. So we need to first design a tank. So we need to figure out the area of the tank, the radius, the height, and how much volume is in it, and also the thickness of the walls of the tank in order for it to withstand pressure. Besides that, we need to know the number of trays to filter the water. And that's everything we need to know. So we don't have any of these things. The only thing that we know is that the volume is 1 meter cubed. So since the volume is 1 meter cubed, 1 meter cubed is not a small number. 1 meter cubed of water is around 1,000 kg or 1,000 liter. So that's a lot of pressure that's going to be acting on the tube. So to calculate the area of the cylinder, or the tube, we have the formula for the area of the tube, which is 2 pi r squared plus 2 pi r h. So h being the height and r being the radius. And since we don't have anything, like we don't have the r, we don't know the r, we're actually trying to find the r. We're trying to find the optimal area, the optimal radius, the optimal. So we're going to take the area in terms of the radius. Since if you increase the radius, you need to decrease the height. Okay. And if you increase the height, you need to decrease the radius. So for the area to be optimal. And for that, we bring in the volume and we put it inside of the equation so that we can solve. So since we know the volume, we put it into the equation, and h is basically equal to this, which is v over. So the area, the h, the height, is equal to the volume over pi r squared. So we can just substitute that into here instead of the h, and this is going to be equal to 2 pi r squared. If we cancel the r with the r and the pi with the pi, we're left with 2b over r. And then now we take the derivative of the entire formula. So we're left with this formula and we need to take the derivative of it. Why are we taking the derivative? We take the derivative to find the minimum amount that we need for the water. Okay, so basically, any place where the derivative is zero, that means the slope is zero. Okay, so if we equal this to zero, yeah, if we put this equal to zero, that means that we're getting the minimum amount that we need. So this is basically the most optimal amount of radius that we can use for that specific volume and that specific height. So we equate the entire formula to zero after taking the derivative, and we solve casually here. So and we get so if we take the r squared to the other side here is going to be 4r cubed. So 4 pi r cubed is equal to 2v, and then we take the 2 pi to the other side. Now we have r cubed equals to v over 2 pi, and we take the cubic root of both of them, and now we get r is equal to the cubic root of v over 2 pi. So we substitute the volume in, which is 1 meter cubed, and we get the radius that we need. So the radius that we need is around half a meter. Okay. So next, now we find the height. So now since we have the radius, it's easier to find the height. So since volume is equal to pi r squared multiplied by the height, we know that the height is going to be equal to v over r squared multiplied by pi, since we did that earlier. And since the r cubed is equal to v over 2 pi from the previous formula, v is equal to 2 pi r cubed. So if we just substitute this v value here into the h formula, so now we get this. H is equal to 2 pi r cubed over r squared multiplied by pi. And if we just cancel these, so we cancel this with this and the pi with the pi, we are left with 2r. So that the height is equal to 2 multiplied by the radius. So it's basically double the radius. Okay. So now that we found the radius and the height, we can find the area very easily. We just substitute everything into the area formula, and we get an area of 5.5 meters square. So this is the area for the cylinder that we're going to use. So next, we need to calculate the hydrostatic pressure. Okay, that is going to be acting on the insides of the cylinder. So to calculate this, since you know how the water at the top is like, and at the bottom is not going to have the same pressure on it. So whatever at the bottom is going to have the highest pressure, since you have all of this water pushing on the bottom of the cylinder. So we expect a change in the pressure as we go down, as the depth increases. So if the pressure increases with depth, we need to take the definite integral of this of the formula of the force in order to figure out the pressure at different depths. So right here, as we can see, so we have here the density of the water, and we have the gravity, which is going to be the acting force, and then we have the height multiplied by y. Y is basically a point at in the depth. So height h is going to be the depth here. Okay, y is just a point in the depth. So let's say y equals to 0. At y equals to 0, this is going to be the top of the cylinder. And at y equals to h, which is the height, so which we just found was 1.084 meters, this is going to be the bottom. So this is basically calculating the depth. So it's the other way around. So as we go down, the depth increases. So the number is going to be increased. So this is going to be 0, and this is going to be h. Okay? And the same goes for the width, basically. So and the width is basically equal to the circumference of the cylinder. So 2 pi r. Okay. Um. Okay. So next, we just substitute everything. So we have the density, and we have the lower limit and the upper limit. As we said, from it's going to be from 0 to h, and we have the gravity value, and we have the 2 pi r, which is the circumference. So we since we're taking the integral, we take all of these to the other side and we keep the y. We take the integral of the y, so it's going to be y squared over 2, and then we substitute the value for the h here, and then we substitute 0 into the formula and we get 0, and then we substitute 1000 or 1.08 sorry, into the y, and we get this. So after we got the number, the value of these together here, now we're going to multiply it with this after negating. So minus 0 is going to be the same number. So we get, after multiplying everything together, we get around 21,168 Newton. So this is the force that's going to be acting generally on the inside of the cylinder. Okay. So to account for that, so we need to find a good material for the cylinder and for the tank. So the things that we're going to be looking for is that the material must be strong, that it should not leach harmful chemicals into the water, so the water stays drinkable, and we need it to be durable and resistant. So and we need it to be cost effective. So it should be practical, and relatively easy to source. So the material that we have chosen here is a very famous one, the high density polyethylene HDPE. So specifically grade 100, PE 100. Okay. So this material is excellent, has excellent strength for its weight, and naturally safe for potable water, and it's very tough and resistant to impacts and chemicals, and it's relatively inexpensive. So it's quite cheap to manufacture. So next, we are going to find the thickness that we're going to use of this material. So in order to find the thickness, we first need to find the pressure. Okay. So the acting pressure at the bottom of the cylinder is going to be equal to the density multiplied by the gravity multiplied by the height. Okay, or the depth. So we just use the exact same formula that we used earlier, just without the width. So this is going to be around 11,468 pascals. Okay, so this is the amount of pressure that we're dealing with here. So the tensile yield strength of HDPE. So the tensile yield strength is basically how much pressure do you need before the material is basically bent or is disrupted. Okay, so the amount of pressure that you need to apply on this material HDPE is 23 megapascal, which is quite a lot. So this tells us that this material is very optimal for this project. And then we have the factor of safety. So this is 3. So the factor of safety is basically like any variations in manufacturing or any like anything unexpected that can happen to the pipe and the corrosion if there's corrosion, but there's no corrosion for this one since it's plastic. So any degradation basically that might happen to the plastic. Okay. So now calculating thickness. So knowing the values that we know. So we substitute the pressure multiplied by the radius that we have found earlier, and then the factor of safety over the yield strength, and we get 0.81 millimeters of thickness. However, this is only enough to withstand the water. Okay, so this is going to be enough to withstand water. It's very thin. Even if you think about it, it's going to be very thin. It's very breakable, but it can withstand water. So more realistically, we need to increase this thickness in order for it to withstand pressure from other things, like handling, etc. Because we're not only dealing with water. So more realistically, we're going to use 6 mil, okay, of things. And then lastly, we calculate the cycles. So the number of trays that we need to use. So for the concentration, so we have the initial concentration, which is 600. So it's going to be 600 multiplied by R to the power of N. Okay, this is a series. This is a sequence. Okay, so R is the radius. R is the basically how much is the reduction. So since we know that decreasing this by 600 by 60% is going to get us to somewhere around 10 milligrams after a certain n number of cycles that we don't know. So our goal is to get to the 10 milligrams, right? So we just put the 10 milligrams here, okay? And then we put the value of the reduction, which is the negation of 60%. So this is going to be 40%. So after you remove 60%, you're left with 40%, and this is the value of the R. So we just multiply the concentration by the R, which is the number that we're left with after negating the 60%. And so 600 multiplied by 40% to the power of n. Okay, and we don't know what n is yet, but we're trying to figure it out. So we just solve naturally. So we take 600 to the other side, and now we have 0.40 to the power of n. And in order to take the m to get the value of n, we use the property of the logarithm ln. So we put ln in both sides, multiply both sides by ln, and now we can use the property of ln and take n right here. So now n is multiplied by ln. We take ln to the other side. Now, since we took it to the other side, the value is going to be negative. So we reverse the inequality. So after dividing the values, we get the number of n. We get the value of n, which is 4.469. And then since this is the number of trays, it cannot be a fraction. So we just round it up. We always round up in this situation. So we round it up to 5. So now n is equal to 5. So we used five cycles basically, 5 trays, and we can see here how much is the decrement in each cycle. So firstly, we go from 240 to 96 to 38, and then to 15, and finally we get to the desired number, which is 6.1, which is less than 10. Okay, which is what we want. Okay, so finally, this is everything. So this is the conclusion. So we have designed the area, we have designed the thickness, we chose the material, and we also designed the trays. Okay, so this is a full design for the filtration system that is usable, and yeah, that's everything. And thank you for watching the presentation.